Hi, good evening, everyone. Thanks a lot for joining in for the session. We shall start sometime soon in a few minutes. Um, as for today, we have switched the topic that is going to be on Friday. That is basically EV charging that I've switched from the day 5 to day 3. The day 5 will be handled by Krishna. That is on powertrain calculation using an Excel sheet. So that would be a practical session that will be held on Friday. Yeah, so you could look forward to attend the session with Krishna on Friday. So I would be continuing the session ahead from today on EV charging. Cool. So just checking out how many people are there. All right. So just before we begin, want to check. I hope you received the emails to join the session today. Just do please confirm if you have got emails. I'm not sure if everybody have got the emails to join the sessions. So anybody, if you have received it, please do confirm that you have received the email. Okay, so about 3 minutes to go. We will begin the session on chargers today. Okay, so if anybody have any questions from yesterday's session, please do drop your questions on the chat box. Or if you have any questions for today, please also do drop the questions on the chat box. I will be able to take those questions and try to address now, or possibly we can address by end of the session too. So by the way, yeah, good evening everyone. Wasant, Abhishek, Vardhan, Prakriti, Karan, and Anup for joining in for the session. Right, so cool. We shall start in the next 2 minutes. So until then, just relax a bit. Today's session would be about 30 minutes to 40 minutes, and then we can have an extended discussion for the QA. So we will talk extensively about chargers and their types, and also some of the things behind the screen on technology of charging, some standards that are involved, and what would possibly take to build a charger altogether. All right, so that's something that we're going to discuss today. So not many slides for today. So we have about I think 8 to 10 slides as in simple, and then pretty much in a graphical way to keep it more engaged and understandable, the exposure of charger systems. Right, so I believe my voice is audible to all of you. Just to confirm if it is audible to all of you. I think we just are good to begin in a few seconds. Okay, so some more people have joined in. Jagat, Nuruddin, Mo, welcome everybody. Samir for the session. Cool. So it's 5 p.m. IST. So let's begin ahead at the session for today. We'll just keep it recording. All right. So good evening, everyone. Thanks a lot for joining the Foundation to Electric Vehicle Subsystems and Technology course. It's on day 3. So we have a topic called EV charging. We have switched the topic for today, which is basically we had a topic on today was motors and controls, and the topic on the charging was on day 5. So I've taken that topic and I have shuffled the topic with Friday's session. So where Mr. Krishna would be handling the practical classes using Excel sheet, how you can actually calculate the component sizing for a motor, such as torques and stuff like that. So keeping that on Friday. So we'll just talk about EV charging technology today. So thanks a lot again, everyone who have joined from all the places across the world. So when we talk about chargers, actually chargers are more required than even cars as far as the requirement is needed today. Because as you build up the electric vehicles across the cities, so you also need to build up the charging infrastructure too, because that will play a very vital role. And today, everybody is concerned about range anxiety, and the topic, the term is defined when you're obsessive about how much kilometers you can get in a single charge. So if there's a technology that can charge the battery quickly, and that means not only the charger can do that, but also the cells should be able to take up the charging. Your thermal management should be able to manage the battery to take up that quick charging. Because when you do a fast charging, you're definitely going to heat up the battery very, very fast. And there should be enough cooling for the batteries at that time. So it's just not one technology as charger, but it also need to be with your cell at a very fundamental electrochemistry and also at thermal systems as well. So I think apart from it, we have all the electrical systems that are already available because we have HV cables and HV technology already available in different domains currently. So as just an overtake, so it's not just only the chargers that are not available today, but also the technology of batteries that need to be available to get charged quickly, and also anything else in thermal management system or any of the peripherals that are required. So for the charging technology. So as far the charger is concerned, so we have two type of charging. One is called AC, slow charging. Other one is DC, fast charging. All right, so that you see on the screen here. So AC and DC charging. So what exactly happens here is, if you take a country like India, so we have 220-volt power supply, all right? And typically what we get is a single phase AC for our home applications. And if the load is high, they can also add you another phase, and they can give you multiple phases too, depending upon your requirement. But if you go to a larger applications, you can also get a 3-phase AC, right? So, and then industrial applications, they can supply you a 440-volt. That is a typical standard. So we have limitations on voltage available. Either it is 220-volt or it is at 440 volts, right? So this is the voltage that is available at the grid, right? So then you can charge the battery using that available source as a grid. So what exactly happens in this part of it is, so you can either charge the battery, like how do you charge your mobile phones, right? So you just have a small brick that is like a charger. So you get a 220 volts, and then you always connect that to a small pin that gives you about a 6 amps at max, typically 5 amps. That is what it is. 6 amp is the rated one, but you get about 5 amps. So that's possibly about like a 1.3 kilowatt nearly. And then if you have a larger socket, that's about like a 15 amps, that you possibly get about 3.6 something kilowatt. And if you go for a higher applications like a 440 volt, you can get the amount of output can be very largely varied in any different manner. So typically this input could be called as a slow charging in the country like India. So that is what comes as a part of our AC charging between 3.6 kilowatt to 11 kilowatt. 11 kilowatt, we may not have availability at India right now, so we would possibly have about 3.6. They can also like put two chargers, like something like this. There are some optional, designs where you can go for it, but typically AC charging happens at 3.6 kilowatts because the available grid itself is limited to provide you a 3.6 kilowatt with a one pin. Right. So this is on the AC slow charging, right? So what exactly that is on the power ratings of the system. Then if you go a little in technicals, so let's talk about available source, right? Let's say it's 220 volts. Let's start from that point, all right? But the battery which is sitting here, let's say it is a 440 volt, correct? So you have 220 volts here, and but you require 440 volts that need to be that the battery need to be charged that level. So what happens in this? So there's a voltage difference between these two, right? So there's supply is 220, but your requirement is 440. So that is what one of the component functionality of a charger is. And the battery is a DC, right? So you can only charge the battery through a DC source. But you're supplying an AC from the grid. So you need to convert the AC to DC, all right? And then you need to regulate that. You need to boost the DC or buck the DC for your requirements. Or for example, if you take this battery is only 48 volt, all right? So let me just rephrase this through a better explanation. So availability is 220 volt, right? But your vehicle possibly have, let's say, 48 volt, or some big vehicle may have about like a 440 volt battery pack. Okay, this is for a car, and let's say this is for the scooter, right? So, but the available grid is at 20 volt. This is AC, and this is DC. Correct. So the functionality of a charger is to convert this AC to DC, right? So that's the first and foremost functionality of a charger. So before it does it, it also need to do some filtering and also manage the variations, because you would have a lot of variations. That is because you don't get to 20 very straight, so you would have some variations in the grid. So you need to take care of that variations. You can call it as a filtering. And also you need to have some safety circuits in between that can disconnect the charger if there is any fault in the charger or the fault in the battery or fault in the grid or any of those things, right? So you have some circuit for filtering, then you have circuit for disconnection, and then you have a AC to DC inverter. So then you need to either buck or boost this to required voltages, right? So because as I said here, you have 48 volt requirements, you also have a 440 volt requirement. So you have to you take the AC and you bring it to DC. You can also regulate the given output here itself, so what you want, but you could also go for one more step to regulate this DC to DC. And then you need to control the output of this DC, right? So let's say now we have now the say AC is 220. You possibly have made that to let's say uh, 96 volts DC, and this is AC. You're converting that 96 volts to 48, and this is the volt value, right? So this is DC in here, and you need to give an output in a very specific fashion, because I might have explained the concept of CCCV, right? So constant current and a constant voltage region, which is here. So this is the standard charging profile for any lithium ion battery. So you need to ensure that you are supplying the current and a voltage in this specific fashion to the battery pack. All right. So you are supplying 48 volt, but the value of current that you're going to supply to the battery should be regulated. It means it need to be controlled in a very specific fashion. So that is what happens inside another circuit, which is basically a control circuit. So it is regulating the DC, and then you give an output to the the battery pack. So then again, you have some other controls and which take care of taking an input back from the BMS to check whether the battery temperature and if there is any faults in the battery circuit while it is charging, so that it will stop the charging process. So this is typically happens across any charger, any hardware of a charger. So if we can just explain you again. So we have an available grade, which is at 220, and you have the filter circuit, which takes care of filtering the input variations. Then you have a disconnection circuit, which takes care of if there is any fault in any of these further systems. So it will just disconnect the charger from the rest of the circuit. Then you have the AC/DC, AC to DC, inverter. So then you have DC-DC converter. Then you have a controlling circuit that is part of this whole ecosystem, whole subsystem, and then it gives an output to a battery. Okay. So this is technically what is there inside any charger. So if you are supplying that to a car which is at 440, you need to convert any of this voltage. Maybe you don't do it at 96. You would possibly still try to keep it at 220, something like that. And then you will boost that to a available 440 volt. So cool. I believe I was able to give an explanation on what exactly happens technically inside a charger. So the AC is available. You need to convert that to DC, and you converted that to DC, but you need to provide the input to a charger for a defined voltage. So you need to, again, if possible, require either bucket or boost it. And then you need to regulate that exact amount of current that goes into the charger, because you have to have a specific profile of charging, right? So that is taken care by the control system that comes as a part of the power electronics. So I think that has been very clear as a part of this learning till now. So going ahead, so that is what happens on your onboard charger. So when you connect this charger to the grid, right? So you would do all this conversion. So you would do filtering, you would do safety cutoff, then you would also do AC to DC conversion. Then if it is required, you would do DC to DC, and then you have a control circuit which takes care of regulating, and then you have an output that goes to the battery pack. All right. So then you have a communication system, maybe through CAN or anything like that. So which constantly monitors battery temperature. It also constantly monitors any faults. If there's anything found like that, then the charger is disconnected from the charging, even though it may be physically connected, but there is no input that is going into the battery pack. All right. So that's typically happens as a part of your the onboard charger. I believe this has been understood. So now imagine if you have requirement, right? The battery is somewhere about 100 kilowatt, right? So if the battery is 100 kilowatt, if you want to charge that battery by 3.6 kilowatt input, all right, so it's like 100 divided by 3.6, even though there are conversion losses and efficiencies involved in whole place. So that would be somewhere at least about 36, 70. So at least about 100 hours. All right. So you require a lot of time if you charge the battery using AC charging. And again, this is ideal calculations. You have conversion losses, and then again, battery cannot be charged 100% efficiently. So there are a lot of losses also involved in here. So maybe the chargers are, let's say, like 85% efficient. And then the battery is possibly about 15%, 95%, sorry, 85% efficient. So again, you lose about another 30% in here. It means it will possibly take you about like a 120 hours for charging. So it means it's too slow to charge. The AC charging is too slow to charge the battery. All right. So you wanted something that happens quicker. So that's why you've gone for a DC charging. Right. So what happens here? The only difference that you see, the supply goes to a charger here, and then it goes to the BMS battery pack directly. But with a DC fast charging, what happens is whatever you do here, all right, that everything you do inside this charger itself.
So, which is outside the car. All right. So, but the values of input current and input voltages are very, very different. So, you're possibly supplying about 440 volts or somewhere about 600 volts input to this charger. Okay. You need to have a dedicated power supply lines from Bescom or whoever supplies to the whoever supplies the electricity. So, typically, these supplies are available at large, industrial areas, or it is available at large buildings where they have to supply a dedicated line so that for example, if you take an industry, their requirements per hour would be like 100 kilowatt. So it means it's a very large amount of power requirements, right? So voltage is still 440, but your current requirement for 100 kilowatt is like P is equal to V into I, right? So its power is about 100 kilowatt, and your voltage is about, let's say, consider for 400. So you have very large amount of current flowing through it. It's about 250 or something. So it means they have to supply a large amount of power to the industrial area. So they have a larger power inputs to the industrial hubs. So that supply is given to the DC fast charger. And this also does an exact same thing. And it takes care of converting that AC to DC, and then it can buck or boost the DC, and then it also regulates that output, and then it gives you to the vehicle, which is basically the battery directly. So there is no onboard charger being involved in between. So this just becomes idle. So that's why there are two ports, right? I'll come to that. There are also chargers, so there is only one port for the fast charging. In some cases, like if you use a CSS, which is a European uh, plug, you can also do with a single plug. But typically, all the other plugs, vehicles will have two plugs, or else sometimes even the Teslas have one plug, which can take care of slow charging and also the fast charging. But typically, there are two plugs. One is for slow charging, one is for fast charging. Okay, we'll talk about that in the rest. So this is a descriptive image of what I was trying to explain. So you get a power supply, right? So you're giving the input to the battery pack. So inside the charger, which is basically onboard charger and offboard charger. Typically, in automotive applications, we have an onboard charger for AC charging. So you have a power protection circuit, you have EMI filter, your rectifier, then your DC to DC converter. So you're converting AC to DC here. You're rectifying, uh, uh, you're converting DC DC and regulating it, and then giving it to the battery pack. All right. So then there's an inputs coming back from the battery pack, such as your voltage, temperature, and rest of other values for any of the monitoring system. If there is something goes wrong, it can cut off. So if you go to a fast charger, so it's exactly in same topology. Like I would say, not topology and overview. It's the same way, but the only thing is you have a larger input here. When and anything is larger in input value, so it can be very susceptible for dangers. So you would have to take care of little more precautions to ensure that there is enough safety and nothing happens for the high voltage circuit. So it's exactly the same in terms of the way it looks like. So you have input, so then you have RCD, which takes care of your disconnecting the circuit. If there is something as a fault in the circuit, you do a EMI filters just to take care of variations, and also any harmonics, any magnetics that can be influenced in the circuit. So you have rectifier, you have PFC, then you have DC-DC converter. So then you're supplying that DC-DC output power to the vehicle between any regulated voltages. So the good thing about a fast charger is it can adopt the voltage value as you possibly require for your vehicle. So just to give you a brief understanding on that is, let's say you have Tata Nexon, then you have Mahindra E2. Oops, sorry. So maybe there's an mg electric, and then whatever it is, let's say there's another some Mahindra XUV electric, something like this. All right. So, but you all of them have to be charged with same fast charger, correct? So I want to connect the Nexon to fast charger. I want to connect the E2 go to fast charger. I want to connect MG to that and XUV to that, and maybe even let's say Tesla. All right. So the discussion here is the Tata may have the battery pack voltage at 430. The E2O have 48 volt architecture, also a 72 volt architecture. So MG possibly have 320. I'm just giving rough numbers. Tesla has somewhere about let's say 480 volt, and XUV has possibly about like 260 volts. So this is the voltage, like values of the battery packs that each of those manufacturers are using. So the charger, which is basically the fast charger, should be capable to supply the required desired voltage to that vehicle, what it requires. Right? It just can't always constantly say, "I'll give you like 400 volts." Right? So it won't be a suitable application. So these are some things which are very unique about a fast charger. So you have a compute like ECU, which is here on the fast charger. You also have either VCU, vehicle control unit, or any other intelligent system which is connected to a BMS. So what happens is that the fast charger and let me just take another color. The ECU, which is in the fast charger, and the VCU in the vehicle, they both will talk to each other first. So they both will communicate to understand what should be the charging voltage, what should be the charging current, all right, and what is the battery pack temperature. Is the vehicle is in good condition to get charged? So a lot of these communications happen between the fast charger, all right, and the vehicle. So when they both talk to each other, again, there should be a communication protocol, right? Typically, the CAN is a typical communication protocol. It also involves whether the plug is connected properly. They can check with the proximity sensor, and they can run some pilot lines to check if everything is connected properly. A lot of these things technically happen in the back end of a fast charger. So it's slightly advanced than a normal average charger that comes with a car or a bike. All right. So this is what happens. So you need to take care of certain things more than what is just required as a very simple low voltage slow AC charger. So let's go ahead. So we have a variety of chargers. For the God's grace, nobody has agreed to make everything unique and same. So we have different type of chargers. There is some typical, very well known Fallout charger is J1772, and these are the chargers which is for AC. That means slow charging. In Japan, also people are trying to majorly use this. If you see Aether has the SAE J1772 charger, and it is pretty sufficient. They have a level 1 AC, level 1, level 2. This is level 1 and level 2 AC charger is by SAE. And then in Europe, they have this name called whatever the name, however you spell it as. So, and then China has GBT architecture. So Tesla has this design except specifically EU market. In Europe, again, you have fast chargers. This is CHAdeMO, and this is CSS2 and GBT. So the unique thing about CSS is like the the specific standard which followed majorly in Europe and North America. The advantage is you can also do a slow charging with this, because if you see, it resembles SAE J1772, but it also has a two major DC inputs. This is basically like a fast charge, and this is a slow charge. So one connector, you can also use it for slow charging. You can use it for a fast charging too. So that is a good thing about CSS. The CHAdeMO has a very unique only used for the fast charging. GBT is also can be only used for the the fast charging. So if you see here and there, these two plugs are different. The complexity is something that I want to explain. I believe if I have any image of the car, right? So if you have a same plug, right, because it's going to save you a lot of money in terms of putting that plug in the car. If you have two plugs, again, you may have to put it if the technical requirements are there or commercial requirements are there. But if you are using CCS, I'm sorry, CCS, so then you just need a one connector here, so which take care of AC and also which take care of DC charging, slow charging and a fast charging. But given a circumstance that all your DC chargers has CCS, not as a technology, but at least as a plug, all right, then it solves the problem. But yeah, nobody agrees like that, right? So typical mindset as a human, so or their own standards and their proven technologies, cost of licensing, because these things are not developed by the OEMs. They might have developed by some specific companies. So you need to pay a royalty if you want to use any of these technologies as a part of the vehicle. So that becomes a licensing cost, and you don't want to do that to add your cost into the vehicle. So you would develop something on your own, and then you have to create also the ecosystem for that. Like what Tesla has done, I said, like, boss, I'll just follow my own thing. If you just, I will set up my own chargers. And what they've done is they've given you a converters, like how you have type A to type B to type C converters, right? So they have something like that. You can also connect this charger to that one, and that to a SAJ J1772 or CCS or something like that. So that becomes like your USB type A, type B to type C, something like that. They have an option, or like what you have for a Thunderbolt to USB connection, something like that. So so again, if you talk about standards, there are a lot of standards which drives the charging ecosystem. So there are specific standards in terms of a grid, in terms of the charger, in terms of the software side of it, also in terms of the hardware side of it. This is on majorly in the hardware side of it, and this is on the side of connectors, communications, and vehicle connectors as a part of it. There are a lot of specific standards which drives to ensure that there is a control over the quality, there's a control over the standards, and that's how everything has been driven as a whole part of the charging ecosystem. You just can't just go and jump in select some wire for the charging if you're doing the fast charging or specific slow charging. So you need to ensure that the cable that is selected, the connector which is selected, the communication stack that you have built in to design these chargers have to be in compliances to these standards. Or else when you go for an approval, you may not get the approvals. So that the last part of the chargers is basically your charge begin control. All right. So when you go to a charging station, you connect your bike to the charging station, and then you have to make the payment, right? You have to scan the QR code, or you need to use an app to authenticate the charging, because you need to make a payment to that. A lot of these things happens, right, in the back end. So you also need a charge begin control. So see, you need to enter some OTP to start the charging process. A lot of these things has to be done when you go to a charging station. So that is again other part of the electronics, which could be even HMI. It is basically a human machine interface to show whether it is charging, and percentage of charge has been completed. A lot of these things has to be visible to the customer eyes, correct? So all these things need to be also taken care. They also need some electronics as a part of it. So what goes in making a charger? So obviously somebody need to be damn good in power electronics, and then have to be good in architecture, functional safety, and HV safety, testing, PCB design, EMI, EMC compliances, fabrication, large scale manufacturing in terms of the hardware. And the other side, you also need to be very good in terms of controls and coding, because a lot of the circuits need to be simulated. Maybe not only this, you have something like SPICE-based softwares for simulation, many other things. They need to be good in communication protocols and interfacing software, functional safety expert. Again, there are standards, as I was mentioning about, and the testing of them, software testing and PC-based calibration, design softwares in real time. You can also add like, iOS or Android apps, because that also comes as a part of your charging network. Um, So yeah, the things just goes on as here. You need to have cloud to connect all your data and stuff like that. So yeah, that's pretty much in place. What I want to cover up on the chargers. So I believe it gave you um, a quite fair idea on what is a charger and what comes inside the charger. Then there is an AC charging, then there is a DC charging. So what comes in part of the AC charging, what comes in part of the DC fast charging, and then we also talked about certain voltage architectures. We talked about plugs. Then we talked about some standards. Then we talked about interfacing electronics, and then typical technical requirements to become one of the engineer to work in the areas of charger development. And now we have the session open for questions. So if you have any questions about this topic that we have discussed till now, so floor is open for QA. We'll take your questions for about 10 minutes, and then we can wind up the session for today. So, right. So, anybody have any questions to discuss for today's topic? So, kindly go over and type them in the chat box. I should be able to answer to them with my knowledge. Okay. Just waiting for any of your questions. Okay, unification of charges can be followed in charging arena. Oh, why isn't followed normally? All have different design. Okay, unification is an interesting thing that everybody, if they do it, it's really better. But what happens is, let's say something like Tesla. All right, so they were the guys. They were very high head of technology compared to anyone. So their chargers were already doing 120 kilowatt. At that time, there was no technology even available with respect to EV charging, uh, to implement. So then Tesla has to design something on their own to make it up for what they wanted to achieve. But then later on, things came out slowly, and then like every OEM have to pay a licensing cost to Tesla if they have to use their own their charging connectors. So they would went ahead with somebody else, and SAE came up with something, and uh, and also it becomes a affordability and availability of technology to develop the and also to integrate the components. So China came up with GBT, or also CHAdeMO. So Japan came up with CHAdeMO, and CHAdeMO became quite famous in good time because of its cost and availability and stuff like that. So everything happens with economical approach. Everything happens with commercial approach and availability approach. And OEMs definitely don't want to follow somebody else, and they just don't want that to happen. So a lot of things comes into a picture, uh, in commonizing them, and I believe it never happens that so easily. Right. So is EV system have bright future in India? Uh, we are able to see a huge adoption of technology. I would say if you have seen the sales of vehicles compared to 2020 and 21, in some cities we have seen the increased sales by 500%. And city like Bangalore, we have seen three times the jump in the vehicle registrations compared to 2020 and 21 in the same month. So that means that there is an adoption that is going to happen. But I'm sure there has to be also good products in the market, like Ether, or something which is more reliable. I'm sure there is some cost also that comes along with it. But I think, yeah, definitely as a country, we have huge adoption of two wheelers. that is going to definitely happen, and you see a good sales of uh, Tata Nexon. People have accepted Nexon, and large sales are happening today in terms of volumes. So it's good in that all direction. We could definitely see the the growth of EV sector in India. In DC, fast charging diagram after the rectifier shows a power factor unit for DC supply. Okay, so in DC fast charger, yeah, that is true. If there is any requirements for that, yeah, definitely, it is typically there as any part of the I would like DC circuits too. How India will manage the power requirements? Um, Good question. I think largely it is feasible and things are going hand in hand. Uh, Also, we see some power shortages and stuff like that. But yeah, I think there is no answer. It's like egg and chicken. Um, Things will get cooked when you keep boiling it. So yeah, that's the current scenario. How India will manage. It has to manage, and we would have to possibly go higher for our renewable energy, or anything apart from it would be again creating emissions. So as far as it is concerned, yes, as I said, if you keep boiling, the rice get cooked. So surely, I think something is going to be addressed, no matter that would be if it's a business case problem. So some investors, some companies like what Tata Power has been doing today to set up charging stations. So yeah, things will happen certainly. Um, so I think on the point of input about as a status, I think if you see Tata Nexon, and also if you see MG, both of them are a fantastic product. Hyundai Kona has been released, but a lot of recalls has happened by Hyundai Kona because of certain issues. So as far as currently it is concerned, I think people are considering it as a status, definitely, because if the customer is environmentally concerned, is a techie, is sort of a geek, uh, because if you read some blogs written by the people who owns the car, are typically who are certainly a tech savvy guys, who own the four wheeler because they're spending a decently about 15 lakhs plus to buy any good EV in the market as a four wheeler. And if you consider two wheelers in the market, so I have seen people even not having that mindset of status quo also have brought it, even at villages have seen, and some of the other suburban parts of Bangalore, I've seen people using Ather, even though maybe the price tag is slightly on the upper side. The price is relative though. But yeah, if you see the pricing of petrol today, there is no doubt, and people would opt for an EV and a reliable EV. So I think it should be definitely an okayish thing with EV. I think government, as such, I am not sure. They can what they can do in terms of changing the mindset. I think it's just that possibly uh, government could support industries to set up and better manufacturing ecosystem. That is something challenging today. If they can do that, at least they would help the OEM. Because if you see any small startup, if they want to buy batteries, you don't get it from big suppliers. They would just straight away walk you out of the door because they don't respect or respond to smaller startups. And it's so difficult to see that ecosystem, and that kind of becomes very challenging for small startups to procure components. They would have to pay a lot of money to procure cells from different sources if they have to buy a qualitative batteries or cells. So I think government should actually look deeper into addressing that, because incentives are good. They will keep the incentives today. I'm sure after 2 years they will remove those incentives, because the government earns money by charging the registration fees to customers, right? So they would definitely bring everything back. There is no doubt about they would just keep giving subsidies, but at least they should improvise the manufacturing ecosystem, supplier ecosystem, certification, exposure to the OEMs and startups, better standards of vehicle development, vehicle approvals. There are a lot of things government can definitely improve in terms of what they should do. Um, that may be the major defining factor, and as such, government cannot initiate, maybe push it by telling that okay, you should buy EV, because it may be a bad statement. But yeah, they could do these things. And first of all, they can adopt themselves EVs at their offices and stuff like that. Awesome. So I think that's pretty much what I wanted to address as a part of the session today. If anybody have any questions regarding the session at last, so I would be glad to address. We may have another minute or two to discuss about the QA. So yeah, the floor is open for questions. If there's no questions for now, thank you very much everyone for taking part in today's session. I believe the session was informative. I believe session gave some exposure to technology of chargers and what exactly happens inside a charger and type of connectors, and some brainstorming discussions that we have done now. So if that's all for today, from the questions here on the chat box, thanks a lot everyone for taking part in today's session, and we'll look forward to engage the tomorrow's session. And I look forward to also upload these videos of recorded session in our LMS. If anybody has missed the classes, you can certainly go back and watch them. And also, you can also watch them in our YouTube channel. So subscribe to our YouTube channel, and by that way, you can also get any updates when you're doing a live sessions and stuff like that. So thanks a lot, everyone. It was great interacting with all of you today, and it was fantastic to deliver a session and share our knowledge from our side. If you would like to learn anything on the advanced technical sides of it, we have courses. They can definitely help you to get into an industry or develop systems for applications in EV. So thanks a lot, everyone. Until then, until tomorrow, take care. See you tomorrow. Bye-bye. Good day ahead for you.